Flipped classroom video for Maths AS Unit 1, Factorising Quadratics. So what is a quadratic? Well, you've met them before, but they are in fact a special case of a type of mathematical object called a polynomial. And polynomials are expressions made up of the sum of multiples of non-negative whole number powers of a variable. And so, for example, we have here x to the power of 5 minus 2x to the power of 4 minus 3x cubed plus 2x squared plus x plus 4. And so you've got powers of x, x to the 5, x to the 4, x to the 3, x to the 2. X is of course x to the 1, and the constant even can be considered as 4 times x to the power of 0, because anything to the power of 0 is 1. And there are various multiples of them, minus 2 times x to the 4, minus 3 times x cubed, and so on. And so a quadratic is simply a polynomial of order 2. So anyway, one or two more examples. Well, we'll have a look at the picture of that one actually first. So that is a quintic, quin for 5, and it looks like that. Another example, we have x cubed minus x plus 4, which you may recognise as a cubic, and they can look like that. That's a cubic. And then we have our old favourite 3x squared minus 5x minus 2, which is of course a quadratic and looks something like that. And notice how many peaks and troughs each of these has. If we look at the quintic, we've got 2 peaks and 2 troughs, so 4 peaks and troughs altogether. The cubic has 2 of them, 1 peak, 1 trough, and this quadratic has 1 trough. So, how would you describe a quadratic graph to someone who hasn't seen one? Have a think about that. So, carrying on thinking about what is a quadratic, we can look at quadratic graphs and we can play with these using dynamic graphing apps. So we'll just have a little look at this. And what we've done is we've entered ax squared plus bx plus c into GeoGebra, and it makes a, b and c, the software makes a, b and c automatically into sliders. And we can have a little look at this. So we start with y equals x squared, and we can see that the a is 1, b is 0, c is 0. The expression for the curve y equals x squared plus 0x is because of the way GeoGebra interprets things, but obviously 0x means there is no x, so that is just y equals x squared. And now we can play about with the values. So if we slide a up, we can see it gets sharper and sharper, but it's still a sort of cup shape, or a U, sometimes people think of it as. If we go to 0, we just have y equals 0. But then if we go negative, then we have the upside down shape, or the cap, or sometimes people call it an N shape. And again, if we get more negative, similarly to the positive, it gets sharper. Okay, so let's go back to just straight x squared. And we can see that things happen if we move the b as well. It moves around, and if we go the other way, it moves symmetrically the other way. And it's very interesting, that movement, but you perhaps look at it later on. If we change c, that's the constant, you might be able to think about what will happen there. I'll just pause for a second. If we make c positive, then it simply lifts the graph up. And if we make it negative, it takes it down. So what we can see here is that sometimes the whole curve is above y equals 0, or the x-axis, and sometimes it touches it, and sometimes it touches it or cuts it in 2 places. And this is quite important. If we make a negative, we can make it cut in 2 places like that, and we'll come on to that later on. So we mentioned the shape of it, and sometimes teachers or others call the one that looks like that, so that's with a positive x squared, a cup or u, and the other way up, a negative x squared, we can have a cap or n. So we're going to look at the structure of quadratics, and this first bit is called making quadratics. Now we know how to write a quadratic, so we can make in a sense a quadratic by a number times x squared plus or minus a number times x plus or minus a number, and we'll get a quadratic. But it's quite instructive to look at quadratics in the way I'm about to. So we've just seen that quadratics can either cut y equals 0 twice, just touch it, or miss it altogether. And this can give us a clue to the structure of quadratics. Imagine that a quadratic cuts the x-axis at 2 and 3. And what that means is if we put x equals 2 or x equals 3 into the quadratic function, then it will equal 0. So we also know that if we put x equals 2 into the bracket x minus 2, we obviously get 0. And if we put x equals 3 into the bracket x minus 3, we also get 0. And what that means is if we multiply those two brackets together, we're going to get 0 if we put either x equals 2 or x equals 3 in. So what does that give us? Well, we write down the x minus 2 times x minus 3, and we'll use FOIL. You may have learnt a different method, but this one is first terms, outside terms, inside terms, last terms, and works fine. So the first terms multiplied gives x times x is x squared. Then for the outside we have x times minus 3, which is minus 3x. For the inside we get minus 2x. And for the last terms we get minus 2 times minus 3 is plus 6. Tidied that up and we get x squared minus 5x plus 6. And we know that if we put x equals 2 into that, it will give us 0 because it came from multiplying a bracket x minus 2. Similarly, if we put x equals 3 in, it will give us 0. Okay, let's have a look at the general case. So, imagine we have a quadratic and it cuts the x-axis at x equals a and x equals b. If we put x equals a into the bracket x minus a, we're going to get 0. And if we put x equals b into the bracket x minus b, we also get 0. So this is just a repeat of what we've just looked at, but with arbitrary a and b rather than the 2 and 3 we had before. We now multiply these together, and we're going to get 0 if we put either x equals a or x equals b in. So what does this give us? Well, same job, x minus a times x minus b. This time we get x squared plus minus b minus ax plus ab, and we can tidy that up to say x squared minus a plus bx plus ab. Okay, and that work helps us towards sorting out how to factorise quadratics. So what do we do when the coefficient of x squared is 1? A general quadratic of that form could be written x squared plus alpha x plus beta. And if it can be factorised, from what we've just seen, we could factorise it as x minus a times x minus b. And that would give us x squared plus alpha x plus beta equals x squared minus a plus bx plus ab. Now, it's perhaps easier to think of this now without negatives. So we're going to imagine that instead of a and b being the values of x that give zeros, then it's actually minus a and minus b. So that means we can write x squared plus alpha x plus beta is x plus a times x plus b, and that gives us x squared plus alpha x plus beta equals x squared plus a plus bx plus ab. And therefore in this situation we can see that alpha must be equal to a plus b and beta must be equal to a times b. So, for example, let us consider x squared plus 13x plus 36, and we know that AB must therefore be 36. So we can write the pairs of factors. So we have 1 times 36, or 2 times 18, 3 times 12, and you'll notice that table does it quite systematically, and we can stop at 6 because we'd just be doing it backwards if we carried on. Okay, now we need to identify the pair of factors that add up to 13, and we can see that we've got 4 and 9. The reason for that is that we know that the multiple of x must be equal to a plus b, or the alpha from the previous work is equal to a plus b, so that must be 13, so 4 and 9 do the trick, and therefore we can say that x squared plus 13x plus 36 is equal to x plus 4 times x plus 9. And this is not necessarily new work to you, but you perhaps haven't seen the more abstract start to this. If alpha and or beta were to be negative, this is a little more complicated, and you'll probably look at that in your classroom lessons. So far we've looked at quadratics where the coefficient of x squared is 1, and obviously this doesn't have to be the case. So let's this time imagine that a quadratic cuts the x-axis at minus 3 over 2 and 7 over 5. That means if we put x equals minus 3 over 2 or x equals 7 over 5 into the quadratic, it will equal 0. Now, if we put x equals minus 3 over 2 into 2x plus 3, we get 0. Just have a little think about that. 2 times 3 over 2 is 3, so 2 times minus 3 over 2 is minus 3. Minus 3 plus 3 is 0. And similarly for 7 over 5, if we put that into 5x minus 7, we'll get 0. And you should have a little check of these with pencil and paper yourself. So, in the same way as before, we're going to multiply these out. So we've got 2x plus 3 times 5x minus 7, and the resulting quadratic will give us 0 if we put x equals minus 3 over 2 or x equals 7 over 5 into it. So what does this give us? Well, first of all, we're going to multiply the 2x by the 5x to get 2 times 5x squared. Then we're going to do the outside, which is 2 times minus 7, and the inside, which is 3 times 5. And those are going to be x's. And we've got 3 times minus 7 at the end. So, first of all, 2 5s are 10, 3 5s are 15, 2 times minus 7 is minus 14, and 3 times minus 7 is minus 21. And then we can tidy up the x term. 15 take away 14 is 1, so we can just write x there. So we end up with 10x squared plus x minus 21. Now, in the general case, we can form a quadratic by multiplying ax plus b by cx plus d. And what does this give us? Well, we've got ax times cx, which is acx squared. We've got a times d plus b times cx, written the other way around there, but it doesn't matter, it's bc plus ad, same thing. And we've got b times d, which is bd. Now notice that in the answer to this, as it were, then each of the letters appears twice. Once each of them appears in the coefficient of x, so we have the bc plus ad, but a, b, c and d are all there, but also they all appear in the coefficient of x squared and the constant together, so we have a and c with the x squared and b and d with the constant, so again we've got a, b, c, d. And this is important in factorising quadratics when the coefficient of x squared is not 1. Okay, so let's have a look at that now. A general quadratic of this form could be written alpha x squared plus beta x plus gamma, where alpha, beta and gamma are numbers that we don't know what they are yet. And we've just seen that ax plus b times cx plus d is equal to acx squared plus ad plus bcx plus bd. So this means if we want to be able to factorise alpha x squared plus beta x plus gamma into something like ax plus b times cx plus d, then we also know, it can also be written that alpha x squared plus beta x plus gamma is equal to acx squared plus ad plus bcx plus bd. And that means we can say that alpha times gamma is ac times bd, and we can rearrange them because they're all been multiplied, so we get a, b, c, d all multiplied together. But we can also see that beta is equal to AD plus BC, and now since alpha times gamma is A, B, C, D, we also have alpha times gamma is AD times BC. So again, we can change the order of multiplication. And what that means is that if we can find all the pairs of factors for alpha gamma, then one of those pairs, which will be in effect equal to AD and BC, they can be added up to give us AD and BC. Now, then we can work out A, B, C and D and pop them into there. And then what we can do with that is we notice that the ACX squared and the ADX both have an A in common and an X in common. So we can take them out. So the ACX squared becomes AX times CX and the ADX becomes AXD. Same thing. We also notice that we have BCX and BD, so we can take a B out there, leaving us with CX plus D times the B, and that means we can factorize. So we've got AX times CX plus D and we've got B times CX plus D, so we can put the AX plus B in its own bracket and times that by CX plus D. Now this is hard, but this is A-level. But this will make much more sense if you look at an example. That process, by the way, that sort of middle line in there, it can be tricky, but usually it's relatively or fairly straightforward. Okay, so factorising quadratics when the coefficient of x squared is not 1, continued. Because we know the answer, for our example we're going to use 10x squared plus x minus 21. And we're going to go through the steps. So the first thing we need to do is to find out what alpha gamma was in the old bit 2 minutes ago, and that means multiplying the coefficient of x squared by the constant term. So 10 times 21 is minus 210. The next step is similar to the step we had to do when we didn't have a coefficient of x squared not equal to 1. So we need to find pairs of factors for this product in this case, and then we have to identify the pair that adds up to the coefficient of x, which is 1 in this situation. So there's our minus 210 split into pairs, 1 times 210, 2 times 105, and so on. And because the coefficient of x is positive, that tells us that when we add the pair up, it's got to be the smaller number that is negative. So that means we can put minuses in there, and so the coefficient of x being 1, as I mentioned, so that means we need a pair that adds up to 1, so that is minus 14 and 15. Okay, so we've identified what the two numbers are that multiply to give us our alpha gamma and add to give us our beta. So we can look at step 3, which is we need to rewrite the quadratic using this new form for the coefficient of x. So we have our 10x squared, of course, but now instead of writing 1x or just x, we're going to write that as plus 15x take away 14x. So we've split it into 2 bits, and that all adds up to plus x. And then we have our minus 21. Now we have to separate the quadratic, which is the tricky step I mentioned before. And the 10x squared plus 15x, we can see that the common factor there is going to be 5 for the numbers and x, of course. So we have 5x, and then 10x squared is 5x times 2x, and 15x is 5x times 3. So all that red bracketed stuff is equal to each other. If we now look at minus 14x minus 21, well, we've got minus, because they're both negative, and we have a factor of 7 in common. So we're going to have minus 7 times, well, minus 7 To get minus 14x we need to times it by 2x, so we have that there. And to get minus 21 we of course have 3, so that would be minus 7 times 3. And now we can see the second bracket for each of those, the red bracketed stuff and the green bracketed stuff, is 2x plus 3. So we can now write that as, and complete the factorization, of course, we can say 5x minus 7 times 2x plus 3. And the 5x minus 7, you can see where that's come from, the 5x and then the minus 7. And the 2x plus 3 has come obviously from the 2x plus 3. So that's a good example of how to do it, but you know now also why it works from the abstract working we did a bit ago. And even though that was very hard, if you have noted it down for yourself, then by doing some examples you will illuminate it and it will make sense.